Hello, this is Chun Liu from Open Persistent Data Infra team at FutureWay Technologies. Today I'm going to introduce the QuantaDB, the distributed database mimicking the quantum entanglement in its commit protocol. Before I introduce QuantaDB, let's take a look at its base protocol. It's called SSN Commit Protocol. SSN stands for Serial Safety Net. It's first proposed by Tianzhen Wang at VLDB Journal 2017 in a paper titled Efficiently Making Almost Any Concurrent Control Mechanism Serializable. SSN is a certifier. It's a serializable certifier. It works on top of any multi-version concurrent control protocol, which is stronger than read committed. In other words, read committed plus SSN will get serializable multi-version concurrency control. If you look at the performance, it allows more scheduling than two-phase locking or SSI, which is serializable snapshot isolation. If we look at the right-hand corner here, the x-axis is the allowed concurrency. You can see 2PL here, SSI here. And the y-axis denotes if this protocol allows cycles. If it has cycles, then it will not be serializable. So we can see that SSN can work on top of SI, snapshot isolation. Then also can work on RC, the read committed. So we choose to use the RC plus SSN to give the highest possible performance. There are several things that make the SSN, the original SSN, not suitable for distributed deployment. For example, it assumes a single node. It also assumes the instant state observation via the cache coherency protocol. It uses spin lock in its multi-threaded validator. Also, because it's a shared memory machine, it assumes a single clock among cores. The QuantaDB, on the other hand, is a fully distributed redesign of SSN. Both the sequencer and the validator are fully distributed, targeting deployment ranging from rack scale, which is 1 microsecond end-to-end delay, to geo-distributed, which is normally 100 millisecond end-to-end delay. It also has high performance in throughput and scalability due to our careful design. We can talk about that later. Unlike deterministic database, such as QuantaDB, it can handle dynamic reads and dynamic write set as expected in generic workload. The building model for QuantaDB is the disaggregated compute and storage, meaning that the instance is stateless, the state are stored on persistent media. That enables deterministic commit, fast local replica reads, as well as fast failover. The storage abstraction is persistent log. We achieve low latency with several methods. For example, we use DSSN commit protocol to reduce the number of message exchanges from cross-chart transactions. We also developed a DRAM PMAM native hash table based key value store for low latency key and metadata access. We also minimize the serial execution window in the validator to maximize the validation throughput. Let's take a look at the SSN commit protocol versus DSSN commit protocol. The base protocol is very simple. As we can see from here, that DSSN commit take a transaction, get a timestamp, find out the pi and eta, then verify the exclusion window to determine it's abort or committed. If it's committed, then we update the eta and the pi for the new versions. The commit protocol for DSSN is very similar. The difference from we can see here is the same T, but we introduce I, which stands the shard ID. Also the CTS, the commit timestamp, which generated by the sequencer. It's not generated from each shard. So we take the CTS assigned to the C stamp of each local shard. Then we finalize the local shard, the pi on the local shard, also the eta on the local shard, very similar to the original SSN protocol. Then here we multicast. This is where we differ. We multicast the metadata information of all the eta and the pi's to the peers, the participating shards that involve in this transaction, distributed transaction. After we send it out, we also wait for the peer to reply. Once we get all the metadata information from all the participating shards, we finalize a global pi and eta for this transaction. Keep in mind that this individual shard will execute all this aggregation, and they should come to the same conclusion because the execution, the computation involved is identical because of the associativity property of the min and max. So all the shards will have the same output, draw the same conclusion. So as you can see here, we get the min and max for pi and eta. Then we verify the exclusion window. Then each shard will come to the same conclusion that the transaction is committed or aborted. Then we update the new versions eta and pi as the original SSN protocol. So very similar. This is the overall architecture of QuantaDB. On the left-hand side, we have client, coordinator, and the sequencer. On the right-hand side, we have validators. At the bottom, we have persistent log. And you can notice here that sequencer and the validator, they have clocks is available to them, and all the clocks are globally synchronized among all the sequencers and the validators. The client talks to coordinator, which in turn talks to sequencer to send commit intent. To accommodate or compensate the network latency and the out-orderness introduced by the network, we use reorder queue to accept or reject commit intent. It works very similar to a TCP sliding window, but instead of sliding the sequence number, we have a timeout threshold. The late commit intent will be rejected. Once a commit intent is accepted, then it will be recorded in the persistent log for replay in the case of failover or restart. For distributed transactions, the validator will process them in 3 phases. The first phase is calculating local eta and pi. Then enter the second phase. They will exchange peer info. Then individually and independently, each validator will aggregate the final eta and pi and draw the conclusion to reject or accept the transaction. As you can remember that in the DSSM protocol, because of the associativity of min and max, all the shards should draw the same conclusion for the transaction. Let's look at a concrete example in the next slide. Here we have sequencer which has T1, T2, T3 in that order. We also have 3 shards. The SABC responds for key A, B, and C. LMN responds for key L, key M, key N. And XYZ is responsible for X, Y, key X, key Y, key Z. And here, T1 access A, L, Z. T2 reads BYZ and writes CY. T3 access ACL. We'll be focusing on transaction T2. Let's say the outcome from T1 is here on the right-hand side. T1 access A, L, Z. The pi is 30 and eta is 10. Let's say L is 31 and 11. Then Z is 52 and 32. So when we look at T2, it will first calculate the local eta and pi for T2. So T2 for ABC, we get that its pi is 40, eta is 30. Similarly, T2 is also accessing XYZ shard. So here, XYZ will have eta and pi of 42 and 32. Then we'll exchange the eta and pi's. And the eta and pi's, they will come to the same, they will share the, exchange the peer info so that SABC will 40, 30, 42, 32. Similarly, 42, 32, 40, 30. Then we get the min of the pi, which is 40, and the max of eta, which is 32. Similarly, XYZ also come to the same conclusion and commit the T2. So this is how they independently calculate and draw the same conclusion. The client will see familiar transaction interface. Start with begin transaction, followed by a bunch of read and writes, ended with commit transaction. The reads goes into coordinator, then directly to the storage node. Write is buffered at coordinator until the commit. At commit, the sequencer will generate commit timestamp. A unique number consists of globally synchronized clock plus the sequence ID. Then the CTS read set and write set are sent to the validator or validators in the case of distributed transaction to validate the transaction. All shards involved in the transaction will see the same CTS. Please be reminded that for a single shard transaction, the CTS is not used by the validator. We'll discuss that later. If successfully validated, the write set I persists at home storage node I. Let's go through an example to demonstrate the call flow. Here we have client, coordinator, sequencer, and 2 storage nodes. One is storage device A, which hosting key 1 and key 2. Also, we have storage device B, which is hosting key 3. The client will start with begin transaction, get ID for that transaction, and use the ID to read key 1. The read is forwarded to coordinator, which directly sent to the storage node. Storage node will send v1 and meta1 to the coordinator, which in turn to the client. Client then will write key2 with value 2, then key3 with value 3. Both are buffered at the coordinator. When time to commit to transaction, the commit will be forwarded to the coordinator, which send to sequencer. Sequencer will generate a CTS right here using the globally synchronized clock, then send 2 commits using the same CTS, which is used as a transaction ID in QuantaDB. The first commit is key 1 and key 2, which send to host storage device A. The second commit is regarding key 3, which is sent to host storage device B. At storage device A and B, we first is the reorder queue, which include a delay plus reorder. Then we log the key 1, meta 1, key 2, value 2 with CTS into the persistent log. Then we generate local meta information regarding the key 1 and key 2's eta and pi's. Similarly, we do that on key 3, the storage device 3 as well. We also get the metadata regarding key 3's eta and pi. Then storage device A and B will exchange peer information. So the peer info will aggregate the local metadata information into global meta information. Then we can do the validate TXN using global meta information. Then we can see that the result is concluded. Then we log the result with CTS and all that meta information into the persistent log. Then we send the response back to the coordinator, which in turn back to the client. Because all the participating client validator is guaranteed to send the same result. When the coordinator receives the first result, it will forward that to the client. Then I'm going to walk through the QuantaDB code structure. The QuantaDB is built on top of RAM Cloud. It has its own directory, which is located inside RAM Cloud src QuantaDB. Here, if you look at, it consists of client part and server part. First, we look at coordinator. It's adapt the client transaction task.cc to add QuantaDB specific transaction handling. All the code change is enclosed in ifdef qdbtx. In RAM Cloud, it uses two-phase commit. Here, we only need a single commit to commit a transaction. So the prepare state will always transit into commit or abort decision. Then we take a look at the sequencer. Sequencer is implemented as a library. Client calls sequencer API to get a 128-bit CTS. The upper 64 bits is clocked in nanoseconds plus a delta. Delta represents the expected client-server network latency. Delta is currently hard-coded. The lower 64-bit is the sequencer ID. It's interpreted as a fraction of nanoseconds. Currently, we're using PTP, and later we will migrate to our Symfony. The code structure is for clock. It's in QuantaDB cluster time service.h Sequencer is in QuantaDB/sequencer.h. Then we take a look at validator. Validator has 4 threads. First is the RPC handler, the scheduling thread, the serializing thread, and the peering thread. The RPC handler takes the RPC call from the sequencer, then checking if it's a cross-shard transaction or single-shard transaction. If it is a single-shard transaction, it's insert it into the local transaction queue. If it's cross-shard, it's insert into the reorder queue. We call this receive stage. Then the scheduling thread is only looking at the reorder queue. The reorder queue is sorted by CTS, so any insertion into the queue need to honor that. Any transaction which has a late CTS will be rejected. Once a transaction is accepted into the reorder queue, it will be popped when its time is over. The grace period expires. Then it will be injected into the distributed transaction set. Then we call this sort and wait stage. And we look at the serializing thread. Serializing thread check both local transaction queue as well as distributed transaction set. It has a priority over. It has a priority in local transaction queue. So we're trying to find the first local transaction queue, and as long as it's not blocked by the current active transaction set, it will validate this local transaction. Then it will try to look at a ready transaction from distributed transaction set and add this transaction entry into the active transaction set. Then this particular transaction is scheduled for peer info exchange. We call this serialized stage. Then any transaction that marked for peer info exchange will be handled by peering thread, where the peer info is sent to the peers. We call this exchange stage. And back to the scheduling thread. Once the exchange information is finished, we can conclude the transaction. Any conclude transaction will be inserted into conclude queue. We call this conclude stage. There are also some functions inside RPC handler regarding the missed peer info exchange that is handled by the reply SSA info. Let's take a look at the validator's active transaction set. Because in the serialization window, we can only have independent transactions, which means we can parallelly execute them without affect the outcome of those transactions in the window. So any younger transaction depending on the transaction that already in the serializing window need to queue up. So we introduce the concept of active transaction set to denote all the distributed transactions in the serialization window. To track the active transaction set and block the younger transactions that depending on the active transaction set, we use a counting bloom filter to track the read set and the write set that accessed by all the transactions in the window. So any tuple in the read set or write set of incoming transaction that conflict with the counting bloom filter, which indicating a dependent transaction. So that transaction need to be queued up. If there's no conflict, we'll add all tuples in the read and write set to the counting bloom filter. Once the peer info exchanged, and transaction concluded will remove the tuple from the counting Bloom filter. The functionality is implemented in active transaction set and counting Bloom filter. Then we take a look at the validators distributed TX set. This is a set that contains all the distributed ready transactions. This set is constantly checked for picking the ready transaction to dispatch. That means we add to the active transaction set, participate in peer info exchange, then do the last phase of the aggregation, then conclude. We have 3 queues to categorize distributed transaction set. Each queue has its own counting Bloom filter. We have independent queue. It means it's independent of all the transactions older than itself. We also have code queue that's waiting for transactions in either independent queue or code queue. I also have hot queue that's waiting for transaction either independent, code, or hot queue. You can think of this way as we pre-sort the transactions into different buckets so that it's easier to pick. It's implemented in distributed transaction set. The peer info tracks the information from the peers of each transaction and handles SS info exchange with peers. A transaction only reaches conclusion when all the peer info is received. However, there's a possibility that peer's info message is received before transaction SSN info is sent out. So there's also a possibility a peer info message is lost. So the peer info could move a transaction into alert state, which indicating that transaction needs special care to come to a conclusion. For example, if a transaction commit intent for a particular shard is too late for that shard, but it's not that late for other shards, then because the peer info will not correlate, then the transaction will come into alert state. We also use a hash map KV store to provide metadata and key value access. So it's implemented as a hash table in DRAM or persistent memory. When we integrate QuantaDB with another durable key value store, the hash table based key value store, which the hash map KV store, become a metadata cache. And if the durable key value store is used, KV store need to provide a CTS, commit timestamp, for any value that fetched from the KV store. We have several issues identified but not finished. For example, the chaining of new version of KV. This is not done. Also, the garbage collection of version chain, epoch-based reclamation should be able to do it. And we currently have a mutex in peer info. We're currently working on it. Then how do we compile the QuantaDB? We need to install dependencies, protobuf, OpenJDK, Boost library, libtvb dev, then check out a copy of QuantaDB repository. Then get all the submodules and make test. Deploy QuantaDB, we need to have all the dependency libraries. Then we config DNS and config SSH login and memory limit. Sharing workspace use Samba, config zookeeper, and create a topology file. Please refer to docs, cookbook.md, or ramcloud's documentation. Then we can run tpcc perf test using scripts, clusterperf.py. This example have 3 server nodes, and in memory only, no replications. That's it. Thank you.